Section 16.7, weak bases. Remember, a weak base is something that can grab a hydrogen from water, but it doesn't do it a lot. It doesn't completely do it. So most of the molecules will still be the whatever the form, whatever it is, whatever the base is, but some of them will grab the water from the hydrogen from the water. The water's acting as a Bronsted-Lowry acid, and grab it and will become its conjugate acid, and then leave hydroxide. Okay, because the water was H2O and it took one of the H's, and so it's leaving hydroxide, which is the conjugate base of the water, and then it's becoming whatever the base is plus H plus. That's the conjugate acid. So you're going to have a new K. This is our 17th one. This one is the base dissociation. Remember, all of these are simply equilibrium constants. So you've got a base and an acid forming its conjugate acid plus hydroxide. So that means that these guys are on the top, and this is on the bottom, and this goes away because it's liquid. So they're the same. All of them are the same. These equilibrium constants are all concentrations of the products divided by the concentrations of the reactants. So if you have an example here of ammonia, ammonia is such a classic base. It's the only one you'll remember in the nursing home that's a base, is ammonia. But you have ammonia reacting with water, and the water is going to act as the acid. It's going to grab one of the hydrogens, and then of course the hydrogen is a proton, so you're ending up with the hydroxide as the negative, and then this is going to join with the NH3 and make NH4 plus ammonium ion, and your case of B, which is how much of this base is actually going to grab the water. That's what the case of B is telling you. How good of a base is it? Is it a puny base and only going to do a little bit, or is it a super megamondo base and is going to be completely grab every single molecule is going to grab water? Well, these are weak bases. You have to remember, we're right now dealing with weak bases. And if you know it's a weak base, then this case of B is going to be, rather small. So your concentration of ammonium is going to be rather low. So your concentration of ammonia is going to be higher. So that whenever you have the denominator higher than the numerator, you're going to have a low constant, as you do here. So I think you're probably getting good at these ice tables. So I is your initial concentration, C is your change in concentration, and then E is your concentration at equilibrium. So this takes care of itself. If you've got hydroxide, you're going to be looking for a case of B. If you've got hydronium, you're going to be looking at a case of A. If you're making acid, you're looking at how good of an acid maker is it. If you're making hydroxide, it's how good of a base maker are you making. That's all it is. They're all the same. The math is the same. Okay, so you've got ammonia. Water goes away because it's a liquid. It's not aqueous or gas. Here's your ammonia concentration here, and here's your hydroxide on the end. So you're going to list whatever they give you. You're looking for the pH. Calculate the pH of a 0.4 molar ammonia. So this is going to be your initial, 0.4 molar initial. You're going to have no ammonium at the beginning because none of your ammonia has broken apart. You're going to have about 0 of hydroxide because remember, water can self-ionize, auto-ionize, and so some of that water can break apart into hydronium and hydroxide, but that's so small that essentially you can ignore it. Okay, so that's kind of 0. Well, you're looking at the balanced equation now. I've got a 1 to 1 to 1 relationship. That means for every mole that I'm dropping, because remember, I'm talking about concentration, that's moles over liters. For every mole per liter that it goes down, this one's going to go up 1 mole per liter, and this one's going to go up 1 mole per liter. So your I and your C are now filled in. Add them together. So I've got 0.4 minus X. That's your equilibrium concentration of your ammonia. Then 0 plus X. that's your ammonium concentration, and then 0 plus X, that's your hydroxide concentration. All right, so if I know my K sub B, it's the same as any equilibrium constant. It is your product times product over reactant, ignoring your water. Well, here is what you're going to fill in. You're going to fill in these guys into this equation. So my ammonium, I've got as X. My hydroxide, I also have as X. My base, I'm going to have as 0.40 minus X. And they're going to give you the K sub B. So they're going to fill in this. K sub B is going to be equal to 1.8 times 10 to the minus 5. Okay, so far so good. Now, I can realize now that I've got X's all over the place, and this is already scary because this means quadratic. In order to find X, I'm going to have to solve the quadratic equation, which takes 10 or 15 minutes for me to do on paper. There are quadratic calculators online. You just you're putting your terms, and it's 5 seconds and done. So that's probably what I would do. I'm probably going to fudge it, though. I'll show you how I'm going to fudge it. This X right here is the concentration of hydroxide. And hydroxide is not made very much when you have a weak base, because a weak base is only going to grab a little bit of the hydrogens off of the waters. So it's not going to make a lot of hydroxide because there's not going to be any leftover waters, because most of it's going to stay, in this case, as ammonia. That means this X is very, very, very small. In fact, it's so small that you can basically ignore it. Now, you can't ignore it every single time. That's why I would use a calculator or do it longhand, quadratic. But if you are short on time and you look and you say, this is a weak base. Weak bases don't make very much hydroxide. So therefore, I'm just going to ignore this and pretend it's not there. When I do that, it's no longer a quadratic equation. It's just a square root problem and no big deal. What's the square root of X squared? X. What's the square root of the other side? Put it in calculator, push the square root button, it's done. So I have two sides. I'm going to have X squared over 0.4 equals 1.8 times 10 to the negative 5. Okay, so remember that X is the concentration of hydroxide. So when you do the math, you've got 0.002. Now, I am wanting the pH. I'm not asked for the pOH. I'm asked for the pH. So I can't just take the negative log of that number. I need to find the negative log of the acid, not the base. But remember, they add up to negative 14. So here is the K sub W of water, 1 times 10 to the negative 14. Divide by the OH, and you'll end up with the acid. So remember, it's the concentration of the acid times the concentration of hydroxide equals 1 times 10 to the negative 14. So you use that K sub W to get whatever you want. So I'm going to divide by the hydroxide, end up with the acid, and this is the concentration of the hydroxide. Of the hydronium. Wasn't exactly asked for that. I was asked for pH. So this is H. This is my H plus or my H3O plus. I want pH, so I'm going to have to take the negative log of this. So 3.7 times 10 to the negative 12 in the calculator. Push the log button, then switch the sign to negative, and you end up with a pH of 11.43.